Good afternoon, everyone. The case studies covered in this presentation show how using fiber reinforcement in concrete construction plays a key part of the construction industry's role in this effort, from large-scale infrastructure and industrial projects to small business and residential projects. Sustainability. What does it really mean? It seems that no one can agree on a single definition. However, most leaders and scholars agree that it encompasses social, economic, and environmental dimensions. After doing a little research, I have found that the simplest definition, and the one I like the best, is sustainability is a social goal for people to coexist on Earth over a long period of time. Or in other words, to meet our own needs without compromising the ability of future generations to meet their own needs. And there are so many different aspects to sustainability: renewable resources, waste reduction, carbon neutrality, green building and infrastructure, sustainable supply chain, and eco-efficiency, among many others. The aspect that I am going to focus on today is durability. And in the realm of concrete, durability has classically meant freeze-thaw resistance, but today it encompasses so much more than that: abrasion resistance, flexural toughness, impact resistance, shear resistance, post-crack residual strength, and I think the most important of all, fewer cracks. Basically all of the things that make concrete perform better and last longer. ACI concrete terminology defines durability as the ability of a material to resist weathering action, chemical attack, abrasion, and other conditions of service. With this in mind, I'm going to present some fiber-reinforced concrete projects that demonstrate how fiber reinforcement plays an important role in our industry's durability and therefore sustainability goals. And while this project was placed relatively recently, the Brunswick Terminal of Georgia Ports Authority already shows how fiber reinforcement increases the durability of concrete. This project included roughly 2 million square feet of concrete for various interior slabs on ground and pavements. All interior slabs on ground are 12 inches thick and reinforced with 7.5 pounds per cubic yard of synthetic macrofiber, and all pavements are roller compacted concrete with no fiber reinforcement. Brunswick is the nation's second busiest port for import and export of roll-on, roll-off cargo, and sees a lot of heavy equipment that come through the port. And this includes CAT D11 dozers, which with an operating weight of over 250,000 pounds and steel tracks, are some of the heaviest and most abusive pieces of equipment that are driven on these slabs. The upcoming images were taken in July of this year and show comparisons between the fiber-reinforced interior slabs and the non-fiber RCC pavements, all of which have seen the exact same loads in traffic. These images are inside one of the fumigation buildings, which all cargo must go into for fumigation before being put on a ship. As you can see, the slab shows only minimal wear and almost no damage from the equipment that has driven over it in the 18 months since it was put into service. Compare this to the RCC pavement outside the buildings, where you can see very obvious wear and damage, including abrasion from the steel tracks of the D11 dozers, joint raveling, and pitting of the concrete surface. Time and abuse have shown that fiber reinforcement has undoubtedly increased the durability of the interior slabs compared to the RCC with no fiber. Prior to arriving in landfills, waste is hauled to transfer stations and dumped or tipped onto a floor where it is consolidated and reloaded into larger trucks. These tipping slabs are known to be some of the most challenging slabs in the industry, subject to extremely harsh conditions, which includes aggressive chemicals, impact loads, abrasive elements, and damage from the constant scraping of heavy processing equipment. These harsh conditions accelerate the inevitable deterioration of the slab, and depending on the types and volume of waste handled at a facility and on how well or often the slab is cleaned and maintained, a tipping slab can lose anywhere from 1/4 to 2 inches of thickness per year. Typical damage seen on these slabs are pebbled surfaces with exposed aggregates, holes and uneven joints, and exposed and deteriorated rebar reinforcement, which is not only dangerous, but also damaging to processing equipment. Eventually, the damage dictates that the slab must be replaced. Designing the slab with fiber reinforcement instead of rebar is one alternative to attain a more durable slab and extend its life. And in 2005, the tipping slab at one of the transfer stations for Attaway Waste Services in Georgia had severe cracking and joint issues and needed repair to extend its life. Conventional design and steel reinforcement had not solved the issues they were experiencing, so project specifiers decided to use high-volume synthetic fiber reinforcement, which at the time was fairly new technology, instead of rebar reinforcement. The 7.5 pounds per cubic yard dosage of synthetic macrofiber and a 10-inch overlay allowed them to eliminate all saw-cut joints, which provided further durability benefits to the slab. The topping slab has developed some reflective cracking, but those cracks have remained tight and caused no issues. With the success of this project, Attaway has used the same overlay design to revitalize the tipping slabs at several other transfer stations, as well as for several new facilities. And in 2012, when Dane County in Wisconsin added a new transfer station to their waste facility, they were looking for options to increase the durability and toughness of the concrete for its tipping slab. Project engineers decided to add silica fume to the concrete mix and use trap rock aggregate to increase the concrete's density and abrasion resistance, as well as to reduce its permeability and shrinkage. They also wanted to use fiber reinforcement instead of rebar to both increase the concrete's durability and avoid the eventual issues with exposed rebar. After conferring with their fiber supplier, they decided to use a relatively high dosage of 12 pounds per cubic yard, which allowed them to have a joint-free slab. To reduce the added cost of the trap rock, they decided to pour the 10-inch thick slab in 2 lifts. In the bottom layer, they used local aggregate, and in the top layer, they used the more expensive but better performing trap rock. They maintained the same dosage of silica fume and fiber dosage in both layers to prevent any shrinkage differential between the 2 layers. This site has been surveyed several times over the last 12 years, each survey revealing no cracks and no issues with the tipping slab. The most recent survey was done only 5 days ago, and these photos were taken during that visit, and they pay testament to the durability and sustainability level that has been achieved. As you can see, the building was pretty full, which speaks to the amount of waste that comes through the facility, but also didn't leave much of the floor exposed. The floor that was clear for inspection had no cracks, and the workers attested that they have seen no cracks in the slab. You can see how the surface paste has been removed by the constant scraping of the equipment, and that has exposed the trap rock. The trap rock is doing its job of providing a hard abrasive resistant surface, and the fibers are doing their job of distributing stresses in the slab and controlling cracks at the micro level. To have a heavily used tipping slab last 12 years with no signs of needing replacement anytime soon is quite the success story. This bridge deck in Ringgold, Georgia, was originally built in the 1950s and had been resurfaced in 1997. But by 2001, the resurfacing had already deteriorated to the point of needing repair. Georgia DOT looked to using fiber reinforcement as an easy-to-use and cost-effective method to add a high level of crack control and long-term durability. 4 pounds per cubic yard of macrosynthetic fiber were used in the 3.5-inch overlay. The bridge deck has been surveyed several times since its initial construction in 2001, and this photo, taken at 6 years of age, shows a crack that had formed from the corner of one of the keyways with the approach slab to the edge of the overlay. As you can see, the crack is being held very tight with no raveling. Compare this to 16 years later, when the bridge is 22 years old, and you can see that this same crack is still being held tightly together with almost no raveling. And as early as 2007, you can already see condition differences between the non-fiber slabs and the fiber overlay. While there is some reflective cracking in several locations, all cracks are being held tightly together with no appreciable raveling. At 23 years old, this fiber reinforced overlay is on track to far exceed its design life. In early 2010, Martin Marietta Aggregates were in the process of replacing their pavement at their Columbia, South Carolina facility, which historically experienced a high rate of pavement failures. So they were looking for a reinforcement technology that could help concrete withstand high-frequency traffic and heavy loading without cracking or failure. The traffic at this facility averaged 250,000 easels per year and at times has reached 300,000 easels per year. Much of the traffic is 5-axle aggregate hauling trucks at 3.9 easels per pass. In addition, the area had poor soils with a K value of 100 PCI at best. Their previous pavements had been up to 12 inches thick and would typically fail within 2 to 3 years of installation. The owners and concrete contractor worked with a fiber manufacturer to design a pavement that would achieve the owner's requirement of lasting at least 5 years. Their final design included a dosage of 30 pounds per cubic yard of steel fiber which not only added the toughness and durability that they were looking for, but also allowed them to reduce the pavement thickness by 50%. When surveyed at the 5-year mark, after roughly 1.7 million easels, the pavement was found to be performing perfectly. No visible cracks, the joints have remained tight with no raveling, and although the paste layer has been worn away, there are no steel fibers sticking up. This pavement was checked again at 8 years of age and found to be still performing well and has far exceeded all expectations. As far as we are aware, this pavement is still in place today and has had no issues. When the new station house for Toledo's Fire and Rescue Station number 6 was being constructed in 2012, the exterior pavement was specified and poured with heavy gauge wire mesh. After placement, they encountered cracking issues with a portion of the slab which had to be torn out and replaced. The specifiers and owners discussed alternatives to avoid a repeat of the first pour. After consulting with a fiber supplier, they decided to use synthetic macrofiber reinforcement at a dosage of 5 pounds per cubic yard instead of the mesh. They understood that fiber reinforcement would add a level of toughness and durability to the concrete that the mesh could not. This image shows the locations of the fiber reinforced pavement sections, which are outlined in red. They are the front drive and entrance of the fire station and half of the rear entrance and parking area. These next photos were taken only a few weeks ago and show us some side-by-side comparisons of the fiber and non-fiber sections. In general, they are performing equally well. However, there's a few points that I'd like to make. Much of the original pavement with the mesh is experiencing a considerable amount of pop-outs, which you can see in these photos, compared to the fiber reinforced sections, which have one single notable pop-out. Even if we attribute the pop-outs to porous aggregates, the mix used in the FRC sections had aggregates from the same source, which would create the same issue. Therefore, we can conclude that the fibers are reducing the permeability of the slabs and holding everything together despite the aggregate issue. Finally, the slabs at the front drive, which are fiber reinforced, developed a single crack which crosses from one panel across the joint through the other panel and ends at a construction joint. This crack could be attributed to saw cutting that was performed a little too late or not at the correct depth, to improper soil compaction, to drying shrinkage, or to temperature changes, but it likely occurred shortly after pouring. As you can see, that crack has been held very tight for what could be as long as 12 years. Again, the fibers are performing as they should. A great example of small commercial applications benefiting from the sustainability and durability of fiber reinforced concrete is the Sparkles roller rink in Marietta, Georgia. In 2004, this family-owned roller skating rink needed a repair solution for their cracked and deteriorated floor. The contractor suggested using synthetic macrofiber due to his previous positive experiences with the three-dimensional reinforcement, knowing that it was the best opportunity to approach a joint and crack-free surface on this very large floor. A 4-inch thick topping slab with a dosage of 7.5 pounds per cubic yard was placed, and you can see that it's decorative. The floor is joint-free and approximately 167 feet by 81 feet. The contractor had no issues achieving a super flat finish. In fact, this repair project received the Award of Excellence in the Restoration category in 2004 from the Georgia chapter of ACI. The fiber-reinforced concrete provides a more sustainable and durable floor with less maintenance than other flooring types, such as wood or epoxy. Maintenance of the FRC floor consists only of sweeping and wet mopping, whereas other flooring types also require refinishing every 5 to 10 years. And about 10 years ago, this area of Georgia experienced some pretty severe flooding. About 2 feet of water flooded the skating rink. Aside from cleaning and drying the building and replacing some carpeting, they did not have to do anything special to get the floor back in shape for skating. If this had been any other type of flooring, it would have required extensive repairs and maybe even a full replacement, which would have meant considerable downtime for the business. A visit to the rink in 2022 to survey the floor revealed that after 18 years, there are no cracks or other signs of wear or deterioration, and the owner reported that the floor is holding up very well. This final project is one that absolutely deserves some recognition and is one that might be familiar to some of you. While some aspects of this concrete driveway might fall outside industry recommendations, it does demonstrate the possibilities of what is achievable with fiber reinforcement when everything is done correctly. This driveway was placed in September of 2011 on a compacted gravel base with a heavy mill poly slip sheet directly under the concrete to reduce the sub-base coefficient of friction. A conventional, commonly available mixed design with half-inch limestone chip aggregate, relatively low cement content to minimize shrinkage potential, and relatively low water cement ratio was used. The only admixture was a low-dose superplasticizer. A synthetic macrofiber dosage of 7.5 pounds per cubic yard was added and mixed on site. The driveway is 5 inches thick with a very uniform cross-section and is 10 feet wide, except for flared sections where it meets the road and where it attaches to a turnaround at the top of the driveway. The total length of the driveway is 210 feet, which is joint-free except for a single construction joint at 25 feet and a single tooled joint in the remaining 185 feet, with the longest joint-free section being 155 feet. The surface received a light broom finish in one direction only and a spray-on surface sealer. Traffic load has primarily been residential car and delivery vans. However, a recent construction project on the property brought aggregate tandems and loaded ready-mix trucks on the driveway as well. To date, there are 0 visible cracks in the driveway. The construction joint does open and close seasonally, and the tooled joint in the 185-foot section has activated but not opened. This driveway has served and will continue to serve this owner well for many years to come. In summary, while fiber reinforcement may not be the silver bullet that this industry needs to achieve durability and sustainability goals, it certainly is one of the tools that should be implemented. These projects are indicative of the added durability and life extension possible with the use of fiber reinforcement. We can see that even though fiber reinforced concrete slabs actually do crack, the 3-dimensional reinforcement keeps these cracks tight and the concrete serviceable. Thank you very much.